that will be enough. Okay, so we have covered the first 7 chapters, and now in the last lecture we studied the recurrence relations, and today we're gonna cover chapter 8, graph theory. Okay, and I gave you the lecture note and laboratory, and also I showed you the graph theory homepage that I made. Actually, it's a laboratory. This is the most important definition, terminologies of the graph theory, and graph isomorphism, subgraph, and vertex degree, path, work, trail, and cycles, and distance, and connected graph, disconnected graph, and coloring, and Eulerian graph, and Hamiltonian graphs, and adjacency matrix, and Laplacian matrix, and those are the things that you can find here. The graph. What is the graph? Graph is an ordered pair, V and E. V represent the vertices. The set of vertices is denoted as capital V, and set of edges, set of lines, set of lines called edges. So set of lines are represented by E from edges, and set of capital V comes from the set of vertices. So if you have a vertices and edges that connecting those vertices, then that makes a graph. And this is an example of a graph. We have a vertices 1, 2, 3, 4, 5, and we have edges from 1 2, 1, 3, and 2, 5, 5, 3, and 4, 3, and 4, 5. This is the example of a graph. It has 5 vertices and 6 edges. Okay. Graph isomorphism. Isomorphism of graph of graph G and H is a bijection between the vertex sets G and H, such that any 2 vertices U and V of G are adjacent in G if and only if f of U and f of V are adjacent in H. Okay. Then we call these 2 graphs are isomorphic, which means basically they are both equivalent. When you do it, you just define first, and you should record those to have this. This is isomorphic to this graph is isomorphic to this graph. That's why. Yeah. So it looks different, but it's just minor move of it, but all the relations are exactly same. And subgraph is a part of that graph, and vertex degree and the number of edges connected to one given vertex, and handshaking problems, and trails, and vertex connectivity, and edges disconnected graph. This is connected graph. Distance, so we will define it in chapter 8, and finding maximum, minimum, and vertex edge coloring. Do colored, and there are many special examples of graph, which including what complete graph, butterfly graph. There are many special graphs. And also there's a this platonic solid. It's yeah. It's also interesting things. But here, here, we're gonna learn about the Eulerian path here. Eulerian graph comes from this Königsberg's bridges. Here, this, we have to define this, and Euler's graph can be made from here. Yes, you should do it at once. And anyway, Hamiltonian cycles, we will learn it, and we will learn about the adjacency matrices. I think that's what we're gonna learn, and then you can go further. Anyway, yeah, you do just practice some of this, and also if you wanna know more about it, then you can you can refer these pages. Anyway, yeah, this you can also, yeah, this is what? This is this is also open introduction of discrete maths. Here, this also shows the graph section, graph series part of this lecture note. Yeah, we're gonna learn all this today. Terminologies and examples are explained in here. Planar graph can be found in here, and colorings, and Eulerian path I explained it here, etc. So yeah, I gave you those informations. Okay, and others will be covered later. Now today we start the graph theory. Now we start. In chapter 8, we will learn paths and cycles and Hamiltonian cycles and traveling salesman's problem, and shortest path algorithms and isomorphism of graphs and Planner's graph, etc. Graphs are discrete structure consisting of vertices and edges that connect these vertices, the edges that connect vertices. And there are different kinds of graphs depending on many conditions, on directions or multiple edges and roofs. Now the many problems in almost everywhere can be solved using graph models. So in here we will give examples to illustrate how graphs are used in those models. Okay. First, we start with the highway system. In Wyoming, in the state of Wyoming, in the United States, this is a map of Wyoming, and there are road highways here and there. We concentrate on this part, central part of the Wyoming, start from Casper here. That can be, this is the central part of Wyoming. Then these are the highways that connect the cities. Okay, this graph, this can be written. This can be written as this. If we only use the vertices, the point, the cities, and the lines as a straight edges like this, then this can be simplified in this. Okay? This Casper's and Douglas, and Gillette, etc. Yeah. And also this graph and this graph are basically same. If you compare it, it's just a reshaping of it, but the ordering of those cities and the connections are basically same. If you see, the land and mud, and land and mud are connected with the edge 12, and wool and gray was connected with E2. Where is E2? Where is E2? Here, black and wool. As you see, this is just, you just reshaped it, but basically those are two. So this analysis of this load situation can be studied in this graph or this graph. Okay, so in a simple way. Yeah, this is an example of graph. It's a graph here. We have vertices. We have edges. Okay. Yeah, the degree of this vertex is 2 because this vertex has 2 edges attached. This is called the vertex, and these are called edges. And this vertex has 1 to 3 edges with it, so the degree of this vertex is 3. So it's called the odd vertex. And these are called edges. And here, all the vertices are connected. So we call this graph is connected graph. There's no direction, so this is called the undirected graph. Okay. Anyway, that's what we're going to learn. Okay. This is one graph of this highway system, and this is an alternative graph of this highway system, but equivalent to the earlier figure. Okay, here's the definition of graph. Graphs are drawn with dots and lines. The dots are called vertices, and lines connect to the vertices are called edges. The edges E1, E2, E3, those are the edges. Those are edges. And we start at a vertex V0 and traveling along the edges to vertex V1, V2, and then we call it is a path from V0 to Vn. If we start from V0 and then move here to here, then we call this is a path from land to bob. Okay. Okay. This is a kind of internet network between the big cities in the United States. And here, so here's the definition of the graphs. And I already explained some. Which can be found in here. Graph G consists of a set of vertices and a set of edges, V and E. And if there is a unique edge E associated with the vertex V and W, then we write this edge is this, from V to W, or from W to V. If without direction, they are same. If it's an undirected graph, they are same. If it is if we have a directed graph later, then this we can give a direction from V to W and W to V. But undirected graph, they are same. In the directed graph, it can be called a digraph. So it consists of a set of vertices V and a set of edges E, or arc. This edge is called with arcs as well, such that each edge E is associated with an ordered pair of vertices. So if there is a unique vertex edge E associated with the ordered pair V, W of vertices, then we write edge is a V from V to W. Okay, so and also we denote edge from V to W. And edge is in a graph that is associated with the pair of vertices V and W is said the incident on V and W. Okay. So V and W is incident if there is a vertex, there is edge from V to W. Okay. And this V and W is called to be adjacent vertices. 서로 가까운 vertices. If G is a graph, then it can be denoted in this way, directed or undirected. Okay, unless specified, the set E and V's are assumed to be finite. And V is assumed to be non-empty. Okay, assume that. Okay, so now graph is an ordered pair of V and E, vertices, set of vertices and set of V's. Okay, graph. G consists of V, which is a non-empty set of vertices, and E, a set of edges. Each edge has either one or two vertices associated with it. It's called its end point. And an edge is said to be connected its end point, as you see in this graph. In figure 8.1.5, edges E1 and E2 are both associated with the vertices pair V1 and V2, and edges E1 and E2 are parallel edges. Here, vertex V1 and vertex V2 has edge E1 and E2. There are two undirected. Then we have two. Then these edges are called parallel edges. And V4, there's no edge connecting this vertex V4. So we call it this isolated vertex. Okay, it is isolated. A graph with neither roof or parallel edges is called a simple graph. Simple graph. This is a roof. Where is the roof? There's no roof here. And if the graph doesn't have roofs or parallel edges like this only, then this is a simple graph. But this part is not a simple graph because it has a parallel edges. Okay, this example 2. Yeah, in the figure undirected graph G consider set this cities, Casper and Douglas, etc. With these are vertices. The cities are vertices. Then highways are edges. We have 13 edges, as this graph shows. Okay, these are vertices and edges, and then makes the graphs. These are equivalent graphs. And if we give a direction from here to here, and from V2 to V3, and V3 to V2, and from V2 to V5, if we give direction like this on each edges, then we call this graph is a directed graph. If we don't have a direction here, we call it is an undirected graph. Directed graph here, and this directed edges are indicated by arrows. For the directed graph, we give an arrow on each edges. And this is an example of simple graphs. This is a simple graph because it has no parallel edges and there's no loops. But this is not a simple graph because there are two edges connecting same two vertices. So it has a parallel edges, so it's not simple. It has a roof like this from one vertex to itself. If you have an edge from one vertex to the edge, one vertex to itself, then it's a roof. So this graph has a roof, so it is not a simple graph. Okay, but in this case, as you see here, there's no parallel edges, but then roof. So this graph is an example of a simple graph. Okay. Here. And yeah, you can read it. And here. From this graph, we can count it from C to E. From C to E, we have the number 5 here. If each edge has a weight, with the numbers like this, we call it is a weighted graph, and the weight of edge is represented as the number on the edges like this. So the weight of edge from C to E has weight 5 like this. And also in a weighted graph, the length of path is the sum of the weight of the edges in a path. For example, from A to D, we can have a path of length 4, and we can have another path from 8 plus 12, which is 20. This weight can be considered as a distance. Okay? So when you have the graph like this, you can go from here to here with these edges, these vertices, and these edges, and or these ways. And then you can count to which the addition of these numbers, if it represents the length, the distance, kilometers, then you can compare which path is shorter than the others. So you can save times. So this weighted graph can be used in the real highway systems when you simply analyze the shortest path that you can choose. So length from the path from A to B, let's see, from A to B, B here, A to B here, then you have the length is 8, and you can have another one which is 2 and 6, which is also 8. So the length of the path from A to B is 8 from that graph. Okay, the path is the graph of figure 1.10 from the E set, and you can make a format like this. And this is example of one graph, weighted graph. And also this is another example of graph. This represents the graph of round robin tournament. When you have a tournament, if you suppose you have 6 teams, you win over the first team win over the others, and the other team win over the others, and the team lose to the others, something like that. You can make a direction for winning or fails. Then you can draw the graph with those tournament, round robin tournament. 그러니까 외국에서 토너먼트라고 하면 토너먼트, 라운드 로빈 토너먼트가 여러분들이 보통 생각하는 리그예요. 풀 리그를 얘기할 때 영어로 라운드 로빈 토너먼트라고 그러고, 여러분들이 보통 토너먼트라고 쓰는 거는 이 싱글 엘리미네이션 토너먼트를 이 토너먼트라고 보통 하는 거예요. This round robin tournament is called a full league system in Korea, and this single elimination tournament system is called just a tournament in Korea. So here, one team win, and if the one team lose, then they just drop off, and only survival teams go up. And you see this type of graph in the tournament, the single elimination tournament in NCAA basketball tournament in March. Final 4, and those comes from this. Okay, anyway, this is also an example of graphs. Mr. E. Kumtek? Sleepy? Okay, and this is also the graph, the example of graphs, example of complete graphs. Complete graphs. All the vertices are connected. Every vertices are connected. This is called the complete graph of size of vertex K1, vertex 3, 4, 5, 6, like this. And this is also an example of graph of cycles, cyclic graph, of vertices 4, 5. We have one cycle connect all those vertices. This is also an example of graphs. This is called the fields. Like you see, it has a center and it rolls. This is an example of graph which is called the fields. W1, W4, 5, W4, 5, 6. Next definition, Bacon number. Have anyone heard about the erudition number? Have you heard about the erudition number? Do you know about erudition? Anyone knows about the erudition? Hungarian mathematician. Have you heard of erudition number? Erudition number is the one that erudition is a very talented mathematician who made great contributions in the number theory and combinatorics. and he is the author, he is himself. Those people who wrote a paper with him, co-author, is called a person with erudition number 1. If somebody who wrote a paper with the person who had erudition number 1, then he is the one who has erudition number 2. And the erudition number 3, 4, 5 are defined in a similar way. Okay, erudition number. And you can easily find he is erudition. Paul erudition, Hungarian mathematician. And Bacon number, he defined it. Actor Kevin Bacon has appeared in numerous films, including Diners and Apollo 13. And a movie star with Kevin Bacon's are Bacon number 1. Okay, some movie star who played a role in a movie with Bacon is called Bacon number 1. Bacon, so Ellen Barkin has Bacon number 1 because she appeared with Bacon in a movie Diner. Okay. Bacon number 2 is a movie star who did not appear in Bacon in a movie that Bacon played, but appeared with a person who had a Bacon number 1. Okay, so higher Bacon number also can be defined similarly. For example, Bela Lugosi has Bacon number 3 because Kevin Bacon played with these 3 persons in a movie, but Dennis Quaid does not appear in the same movie with Kevin Bacon, but he played with these 2, so they have Bacon number 1. Kevin has a Bacon number 0. These 3 has a Bacon number 3 in this figure, and Bacon number 1, and Dennis has a Bacon number 2, and here Bogan has Bacon number 2, and Bella has Bacon number 3. Okay, co-player, and co-player. So Bacon number 1, 2, 3, like this. Bella does not play with Kevin Bacon in a movie, but he played with someone who has a Bacon number 2 in the same movie. So those numbers can be defined, and also those relationships can be drawn in a graph like this, easily understandable with the graphs. And similarity graphs. Similarity graph is constructed as follows. Vertical correspondence to programs, and vertex is P1, P2, P3, where Pi is a value of property I. Then V of G is a set of programs. Then each vertex Pi is assigned a triple P1, P2, P3, where Pi is a value of properties, and so VI's are defined with this. Okay. So with this, we can have an example of a similarity graph. Here, example deals with the problem of graphing like object into classes based on properties of the object. Here, suppose that a particular algorithm is implemented in C++ by a number of persons, and we want to group like programs into classes based on certain properties of the programs. Then suppose that we select as properties as 1 the number of lines in the programs, the number of the return statement in the program, third the number of function calls in the programs. These are examples of similarity graphs, and these are tables that shows it implemented. The number of program lines, statements, and function cells, to compare those. Do you know how they are grading their homeworks? 그러니까 보통 코딩 숙제 주지. 코딩 숙제 주면 채점 어떻게 하는지 알아요? 보통 코딩 숙제 주면은 학생들 코드에서 숙제 내면은 이제 채점 하잖아. 채점 어떻게 하는지 알아? 코드를 그냥 돌려보면 타임이 같이 나오는 것들은 거의 누구 거 베껴서 쓴 것들일 경우가 많아요. 겉은 막 설명 막 달고 그래서 남의 것 같이 보이지만 그래서 자기가 코드를 직접 짜면 그렇게 완벽히 똑같은 코드가 나올 수 없는 게 라인 숫자도 달라지고 이 저기 간의 루프들이 달라지고 그리고 쓰는 펑션들이 차이가 나기 때문에 다 차이가 나요. 그러니까 보통 그런 걸 비교하기 위해서 이렇게 숫자를 비교해 보면 채점할 때 누구 걸 복사했는지 금방 딱 나오게 돼요. This kind of argument can be used on those dissimilarity functions. Yes, this is the other part of it. But we have more interest on the not similarity, the graphs. We are more interested in the graph similarity later. Okay, but so we just skip this part. Similarity, dissimilarity graphs. But this is important. N cube, hypercube. Have you heard about this hypercube? This is a four-dimensional object. Four-dimensional object. Example of four-dimensional object. Hypercube. Okay. And there are many of others. N cube, which is an example of hypercube, is like this. N cube. We discussed one model for parallel computation known as the N cube or hypercube. N cube IN has 2 to the n processors, and vertices are labeled from 0 to 2 to the n minus 1. So we have 2 to the n vertices. And an edge connects to vertices if the binary representation of the labels differs in exactly 1 bit. And N cube, here is first start with 1 cube. 1 cube has 2 processors labeled 0 and 1, 2 to the 1 minus 1, and 1 edges like this. This is 1 cube graph. Okay? And H1 and H2 be 2 n minus 1 cubes whose vertices are labeled in binary from 0 to the n minus 1 minus 1. Okay, here, anyway. I1 is a line. It's a hypercube like this. It has the only vertices 0 and 1, 0 and 1, like 0 and 1. It has no cycles. This is an example of I1. Next, I2. 2 cube, square, like this. We have 2 to the 4, 2 to the 2. So we have 4 vertices with binary notation, 1, 0, 0, and 0, 1, and 1, 0, and 1, 1. So we have 4 vertices and edges connecting these in this way. This is called the 2-dimensional hypercube. What about 3-dimensional hypercube? We have 2 to the 3, 8 vertices with the edges like this. This is 3-dimensional hypercube. Then how we can think about 4-dimensional hypercube? That's what you have seen. And there are explanations. There are more explanation can be found here and there. And here next, from that hypercube we can find the Hamilton cycle from starting from here and then go this way and then 1 1 and 1 0 and 0 0 like this. Then this is a cycle that passes through every vertex is just once without repetition. We call the Hamilton cycle of this 2D hypercube. And for I3 here we can find the Hamilton cycle that starts from 0 0 0 and 0 0 1 and 0 1 1 and 0 1 0 and 1 1 0 and 1 1 1 and 1 0 1 and 1 0 0 and 0 0 0. And that's the hyper the Hamilton cycle for this 3D cube. About 4 cube. We have 16 vertices and 32 edges. Okay, we can level with from this observation. We can think of the order of those 16 vertices that pass through. This is a kind of order. Do the first and then go inside. Okay, combining 2, 3 cubes to obtain a 4 cube. Okay, anyway, so we can think about 3D, 4D, 5D in this manner. So we can analyze the the Hamilton cycles on the higher dimensional hypercubes in that from those observations. Next, complete graph on vertices. Denote Kn. This is a simple graph with n vertices in which there is an edge between every pair of distinct vertices. Here, for like this, we have 4 vertices and it connects every. This is K4. Yeah. From one to the others. Every vertices has 3 edges. Okay, vertex degrees are 3, 3, 3, 3, which means each vertices have a path to all different vertices. So this is example of complete graph on 4 vertices. Next, definition of bipartite graph. Bipartite graph. If there exists a subset V1 and V2 of vertices set V, and those two are disjoint, and union makes all the vertices, then we call this graph is bipartite. If each edge is in E is incident on one vertex in V1 and one vertex in V2. With this condition, we can find V1 and V2, subset V1 and V2 of vertex at V, then we call this graph is bipartite. And you can see some lecture note on those bipartite. This is an example of bipartite graphs and complete graphs. Anyway, this is an example of bipartite graph. This is a one graph. This is a graph. But here, you can find you have 5 vertices, and 5 vertices set with edges can be reorganized as a set of V1, V2, V3, which forms V1, and V4 and V5 as V2. Then this vertex set makes what? Union of these are disjoint, and these are what? The union of these make all 5 vertices in the graph, in the whole this graph, and also there is no edges in between here, but it has all the any vertices, any edges starting from this vertex, this side of vertex, ended at a vertex in the other side. So this V1 and beta satisfies all those relations. Disjoint and unions are all, and every vertex is from one side and ended at the other side. Okay. So this the earlier graph can be considered as a bipartite graph because it satisfies all those conditions. Next, but this graph is not a bipartite graph. The way in example 1.13 he showed it is not bipartite by contradiction. So the way is we supposed by the way of contradiction, if suppose this graph is bipartite, then it occurs of contradictions like this. So it is not a bipartite graph. That's the argument that we did use. You can easily check those. Next, complete graph K1 on one vertex is bipartite. K1 is just this one. This satisfies every conditions because there's no edges. So it's by tautology, it satisfies that condition, etc. Anyway, this is a bipartite. And K1, K1. And K2, this is also bipartite, isn't it? We have two vertices here. Anyway, this is a complete graph, example of complete graph. K3, K4, and K10, K12, 1, and K66 like this. Beautiful, isn't it? As it goes, complete graph. Okay, KMN is another example of complete graph with m vertices in one side and n vertices in the other. Here, this is an example of complete bipartite graph K35. One side it has 3 vertices and the other side has 5 vertices. All the edges start from one side, ended at the other side. This is example of bipartite graph, and every vertices has an edges to all of them, the vertices in the other side. So it's complete. This is 3-5, so it's called K35. K stands for the complete in German language. Okay, next example. Complete bipartite graph on 2 and 4 vertices, K24. K24, this is K24, 2 vertices and 4 vertices. And this is complete bipartite graph. This is also by example of bipartite graph. K23, K33, K35, K26, like that. And this is also, the example of complete. This is not a complete graph, but you can see this type of graph in the real life problems. Modeling the job for which employees has been trained. So this person has been trained in here and here, and this Chen was trained in here and here. So from these observations, with this graph, you can find the best possible assignment of the person that fit with their educational background. I think that's the end of section 8.1. You have a homework on exercise problem 14, 15, and 25, which is very simple. Any question on section 8.1?